Now let's just talk about the majority detector for our neural model. So this is the neural model that we have seen previously, that we have designed it on we have called it on the Verilog on the Quartus. Now we're gonna design a function that detects the majority of the dendrites, how many dendrites are on. So if the majority of bits are on, we should have a function f that will be equal to 1, since this is only one bit. So this is like a function that you're going to show us that we have a majority on the dendrite. So in this case, we're going to only look at the only 3 bits. So this, in your case, this is going to be in your exercise. But for now on, we're going to focus only on these 3 bits. So we're going to create a function that detects a majority of the dendrites when we have only 3 dendrites. So one way to approach this is to generate the truth table for this dendrite. So if you remember, we had dendrite. So let's generate this truth table for the dendrites. So we have dendrite 0, 1, and 2. And here we have merge detect. So this is our function majority detector that will gonna detect if we have a majority of bits on when they are on. So when you have 3 bits, so the function f will be on if there are more than 2 bits. So this is the kind of idea of how the function will work. So now if we generate a truth table for this, we know we have 3 variables. So this is, so how many combinations we'll have? We're going to have 2 to the power of 3, which is 8 combinations that we're going to have. So let's start for our first combination. The first is 0, 0, 0. And when we have this kind of combination, our majority detector function is 0. So 0, 1, 0, 0. This is 2, 2 is 0, 3 is 1, since now we have our majority, and then 4, 1, and 7. It's going to be 1. So this is our truth table for our majority detector. So we can see here we have those 8 combinations, and we have a majority detector only. We have a majority detector when we have 2 bits are on. We have a majority. So this has happened at when we have 3, 5, 6, and 7. Then we have a majority detector. So those bits are larger than 2. Now to generate this function, you can either use mint sum or k-map. So in this case, we're going to use a map, or you're going to call it k-map for the short. So we're going to generate a k-map for this truth table. So we're going to have all these 8 squares on this table. So one way to do this is so we need 8 squares. So here we're going to have our D0 and D1 input, and here we're going to have our D2. So we're going to use something called, on Kmap, we're going to use something called gray code. Since this gray code is kind of a way to start giving those combinations. So the first combination is going to be 0 0. So this means that one bit in gray code, 1 bit at a time must change. So this is 0 0. The second bit is changed when it's 2, when it's 1, and the second bit, so this one must be 3 in order. So you can see this stay the same, only 1 bit changes, and the second one is going to be 2. So this stay the same, this one changes. So this is why it's called gray coding. Only 1 bit at a time is changing. And here, since we have only one combination, so only one, so it's 0 and 1. So now, how we're gonna fill this table is to, so if you can see here now, the 0 zeros here correspond to these zeros here, and this 0 here correspond to this 0 here, and 1 is for all these ones. First of all, you can see this line here is 0 0, so it will become here because here we have 0 0 and 0, and if it's 0 0 1, so it's going to be 0 0 1, it's going to be coming here. And for example, the last one is 1 1 1, so you have 1 1 and 1. So let's try to fill this table now. So it's going to be 0 0 0 1 1 1 0 1. So as you can see, for example, here is 1 1 0, and here we have 1 0, and then 1, and then we have 1 here, so it's 1. So now, how will you get a function from this Kmap? So one way is to circles all the ones together, and you can only circle the ones for the combinations 2 to the power of n. So for example, you can have only circles of ones for 0, 1, 2, 4, and continue. So the power of 2. For example, our first circle, let me use another color here. For example, let's use this blue. So our first circle, that's this one. You can say this is our first circle, our first square of ones. And the next one, we use purple. You can say it this one. And the last one is green. So different color you can see. You can say this one. So let's just write the corresponding functions. So for example, for blue one, you have the function is gonna be. So let me explain how you're gonna get this. So for example, if you see, so we're gonna see which kind of combination contribute to this one. So for example, here you can see, for example, D1, it does not change, but D0 changes. So you can see clearly this one does not contribute to anything to this square. So it doesn't. So we only care for that doesn't change. So in this case is D1, and here for D2 we can see here that is D2 is 1. This function, the first one, is going to be D1, D2, and for example, if we take the green one now, the green one is going to give us, so we're going to see here, D1 changes, so it's going to be D0, D0, D2, and the purple one is going to give us, so here we can see both of them. So you can see D2 changes from 1 to 0, but the D0 and the 1 doesn't change, so you're going to give us D0, D1. So this function for majority detector is going to be for D0, D1, or plus same, D0, D2, or D1, D2. So this is the function that is going to detect a majority detector. So it's, for example, this one or this one or this one. So all of this combination for this function, it will detect when we have a majority detector on this our neural model for the derive. So on the next video, we're gonna code this on the Verilog quarters, and we're gonna write a test bench for this. We're gonna add this function on our neural model, and then we're gonna simulate it to on the model sim and see what kind of results we're gonna get.